Let's take a look here at example number 1 to start to get the sense of how one of these optimization problems actually goes. So let's see what we have here. Remember that the first step is going to be reading the question, trying to understand really what it's asking, and then go ahead and draw a picture to kind of model it. So let's see. A farmer has 2,400 feet of fencing, and they want to fence off a rectangular field that borders a straight river. Now he needs no fence along the river side. And so the question is, what are the dimensions of the field that would ultimately produce the largest area? Okay, so I have a farmer with some fence. He's trying to like build a field or fence in a field, and it's next to a river. All right, so to help maybe try to draw this out, I'm going to go ahead here and just try to create my straight river. So maybe I have something like this. Okay, so in here, we'll have this be the river. Okay. So I'll label it like this. Look at, here's some water. Look at the quality of my picture. It's great. Now I have this river in here, and there's going to be a fence that's going to be kind of built along it, right? So maybe something kind of like this is going to look like the fence. Okay. Now, it's supposed to be a rectangular field, so I know that however long this side is going to be the length of whatever this side is. So for the sake of argument, since I don't know how long this is, let's say that this side is length x and that side is length x. Now this side, it could be the same length as the other sides. There's nothing wrong with that, but it could be a different length. And since I don't know them, I'll just give it a different variable. If it turns out that both these values come out to the same length, then I'm totally fine. So this is kind of the scenario that I have, and I'm interested in trying to make this area as large as possible, right? What are the dimensions? What are x and y? So that the area of the field is as big as possible. So the first thing then that I want to start to do here is to really understand what I'm trying to optimize. And I'm going to write a sentence here to indicate that I found that. We want to maximize the area of the field. Okay, so the moment that I know that I want to maximize the area, let's give that the symbol A, then I need to come up with an equation for the area of the field. Okay, so how, looking at the picture, would I calculate the area of my field? Okay, well that's actually really easy, right? Because if this is rectangular, then I'm just going to do x times y, that's my area. Now what I want to do is I want to maximize A. I want the biggest possible A value I can come up with. And so to do that, I'm going to go ahead and take the derivative of A and then try to figure out where it has mins and maxes. There's just one problem. Right now, I don't really have a formula that looks like a traditional f of x equals, right, and then I have a bunch of stuff with x formula. I want to create an a of x formula, so it kind of looks exactly the same as what we've done in the previous sections. It's just it has an a in the front instead of an f. But the issue is that right now I have an x and a y in here, and I kind of only want one variable. Ideally, it would be great right now if I could only have the variable of, say, x. So I need to go ahead and figure out how I can write this formula with a in terms of one variable. So I'll say we need to write a as a function of one variable. So what I need to do is I need to figure out what y could possibly be the same as, so that way I could get rid of it and kind of update this equation here and work with it now only with x's. Well, if I think about the other information that I have in this scenario, and it's not much other information, the only other thing that I see that I haven't really used so far is that the farmer has a limited amount of fence. There's a constraint or a restriction that the farmer has to follow. The farmer only has 2,400 feet of fencing. Ooh, so this would be interesting. So I could state that we know that if the farmer uses x feet of fence on this side, plus y feet of fence on this side, plus x feet of fence on the other side, that would be a total then of 2,400 feet of fence, right? Like all those amounts together have to use up all the fencing available. So that means that we ultimately have 2x plus y equals 2,400. And notice we could rewrite that to say y equals 2400 minus 2x. I found what y looks like in terms of x's. And so now we can update the value of a. I can now say that the equation a, which was x times y, could be rewritten as x times 2400 minus 2x. Or that's the same thing as saying 2400x minus 2x squared. So now this does look like a function that we've seen in previous sections. And so I can go ahead and think about taking its derivative and seeing where it has mins and maxes. So I'll now say that we calculate that a prime would just be equal to 2400 minus 4x. And if I want to figure out now where this is equal to 0 and undefined, so I'll say a prime is equal to 0 when 2400 minus 4x is equal to 0. Of course, that's whenever 4x is the same thing as 2400, and that's the same as when x is going to be 600. Okay, I can also see here that a prime is never undefined. Okay, great. So I found all of the important critical values. Ooh, and notice, this is the only critical value. Hopefully it corresponds to a maximum. So let's see. Now I can go ahead, I can draw out a number line. I can put 600 on here, and now I can test to see what happens in my derivative. So a prime, and here are my x values. So notice, let's plug in something that's maybe bigger. So I'm going to plug in something like 1,000. If I plug in 1,000 in here, notice I'm going to get 2400 minus 4,000. That's going to give me a negative. If I plug in something maybe say like 1, right, like x is just the value of 1, this is clearly going to be a positive. And so I can see here that I am going to get a function that goes up and then down, and it's a max. But since it's the only value, it is an absolute max. And so I can see here that x equals 600 feet does correspond to a maximum area. It actually works, right? This is great. Now, I should notice here that I haven't quite answered the question, right? Because this question has said, what are the dimensions of the field with the largest area? So I know apparently if x is going to be 600, I get a maximum area. But I still need to figure out what y is. But notice this is really easy to do, because if x is equal to 600 feet, we already know that y was going to be given by this formula right here. Y is equal to 2400 minus 2 times x, so that's going to ultimately be 1200 feet. So we have that x should be equal to 600 feet, and y should be equal to 1200 feet. So we've done it. These are the dimensions that produce the largest possible area. The main key here is to note that what we had to do was to write an equation for the item that we wanted to maximize and then get it in terms of a single variable, so it looked like a function that we've dealt with in previous sections. Now we'll take a look at a lot more examples like this question in the videos to come. And so we'll see a lot of other ways that we can kind of implement this idea and get a lot of practice with these concepts.